Hello, everyone. Welcome back into the machine learning track. I remember that our producer told me just before I started my hosting that we were doing so well on time, and then you get me, and all tracks will, take a little bit longer. Anyway, hi, Johnathan. In this next session, AI in a Minefield learning from poisoned data, Johnathan Azaria, data scientist, a tech lead at Imperva, will present the challenges of learning from dirty data, overview data poisoning attacks, discuss the problem of learning from web traffic, and explain different approaches for learning from dirty data and poisoned data. The virtual stage is yours.
Okay, thank you very much. Thank you. So first of all, I want to thank everyone for joining us. Thank you for joining the session. As mentioned, the title is AI in a Minefield, Learning from Poison Data. This presentation has been a joint work between me and Itzik Mantin. Itzik Mantin used to work for Imperva. He left, but the credit is due where it's due. And my name is Johnathan Azaria. So let's just start a few words about me. I'm a data scientist, tech lead at Imperva. I was a security researcher before that. I am part of the threat research team at Imperva, and I have the best dog. So a quick outline about what I'm going to talk about. So we're going to do a quick intro. We're going to talk about AI risks, AI threats, and specifically data poisoning. This talk is about data poisoning, so I'm going to focus on that. Then we're going to talk about learning from web traffic. We're going to use this as a use case about talking about poison data. How can you poison data when someone is trying to learn from web traffic, and how can you mitigate this issue? And finally, we're going to have a quick summary and conclusions. So we are living in the AI era, right? AI has created a great leap for humanity in many areas. Right? Technology has become much better following AI. AI is basically surrounding us, right? We see it in basic things like electronics. We see it in cars that drive themselves, and we see it everywhere. But one of the things about AI is that it's nothing without data. So you can say basically that we're living in the data era, and data is the new gold. However, when you talk about data, there are some caveats, there are some problems when you try to acquire good and useful data, because that's really what machine learning is all about. It's about using the data in order to create a better model, and if the data isn't good, that's a serious problem. Okay, so let's talk about some risks. Okay, the good, the bad, and the ugly. So first of all, when you talk about AI risks, it's really difficult not to mention a deep fake and just advanced technologies, right? So one of the things about artificial intelligence is that it allows us to do a lot of different things, and that can be used against us, right, or against humanity in general, or just to do things that really aren't good, things that are malicious. So in this example, someone can use deepfake. Deepfake can either be used to just create cheaper scenes for TV or movies to cut production costs, etc. But also someone can basically take someone, okay, take a character of some sorts, maybe even someone like the President of the United States, and make it look like they're saying something that they never really said, which can be used to perpetrate and to spread a lot of fake news that is really difficult to refute, right? Because someone can see a video where the president is saying something. He didn't actually say it, but the video shows that he did. And it's very difficult to contradict when you see this type of video. So that's the first thing when you talk about AI risks. Another issue, which is a very big one, is AI discrimination. Again, this isn't exactly cybersecurity attacks on AI, but it is something that is a big risk when you talk about AI. So AI discrimination is basically a perpetration of biases. One of the issues with artificial intelligence and machine learning is that it basically uses the past, uses data that's obviously in the past in order to predict the future. Now, if this data had biases of any sorts, the model will learn these biases and will act upon them. The model doesn't know good or bad, right? And if it was taught something that has issues, it's just going to use them in order to try to predict the future. So if you have data that has any sort of biases in them, and it can be just kind of natural biases, right? I mean, you think about history. So there were some roles that were played by women mostly, right? There were very feminine jobs, jobs that mostly women filled. And over time that changed. But if you're going to use historic data, the model is just going to learn that some specific jobs are like meant for males and other meant for females, which isn't true, but that's what the model is going to learn. It can also be something a bit more difficult, like actual racism, or just maybe think about someone trying to use, let's say, data from Europe to try to understand, let's say, if a person is likely to be a criminal, yes or no. But instead of using data from the last 10 or 20 years, someone used data from the last 100 years. And maybe got also data from Nazi Germany and some fascist regimes, etc. So that data is going to be terrible, and the model is going to be very, very, very racist and very bad. So this is something that is a big risk when you talk about artificial intelligence. Another thing is evolutional attackers technology. So one of the issues with artificial intelligence is that anyone can use it, right? So it can be used for good, right? It can be used in order to stop attacks, and it can be used in order to do some nice things like cars that drive themselves and whatnot. But also attackers and hackers can use AI and machine learning in order to work more efficiently. So hackers can use artificial intelligence for automation, data mining, and insights in order to quickly crack websites, in order to quickly discover vulnerabilities, etc. And finally, and this is really what this talk is about, there are some AI threats. So basically, any threat that is a threat to the artificial intelligence itself. When you have some sort of a model and you try to hack the model, to crack the model, to attack the model itself, this goes under the category of AI threats. Okay, so and maybe some of you are aware of the Gartner technology hype cycle, which goes something like this. There's the technology trigger. Some technology is being discovered. This technology gets very visible because at some point there's this peak of inflated expectations. Everybody thinks that this technology will solve everyone's problems. And then there's this trough of disillusionment, where people understand that it's not as great as people thought it was. There are some issues, there are some problems. And then you start this kind of a slope of enlightenment, where people start using the technology and understanding that it can be used to solve a lot of problems, maybe not all the problems, but some of them, and eventually reach this type of plateau of productivity, where this technology is being used over time, and as time goes by, it's being used more and more, and to be enhanced until up to a point where basically a lot of people are using it and it's helping a lot of people. So you can do the same thing, only with security. So at some point when you have a new technology, so in the beginning you have zero security, okay, whatsoever, both ways. Nobody knows how to hack it, but nobody really knows how to protect it. Then at some point you start to discover new vulnerabilities. And at this point, really, there's this sort of decline, because you have fear, uncertainty, and doubt, because people are scared of using the technology, because they have all these different vulnerabilities. People don't know what will happen, if it can be hacked, if it can be abused, etc. And then after a while, you start having these new security solutions, and eventually reach this kind of plateau of it's kind of a cat and mouse game, where you have new attacks, and then you find ways to block these attacks, and then you have new attacks, and so on and so forth, which basically what's happening with all technologies, all mature technologies nowadays. Okay, I believe that we're more or less reaching the plateau of productivity when we talk about artificial intelligence. Okay, so AI threats. This is like a classic machine learning workflow. You get training data either from the inside or from the outside. You train the machine learning algorithm and you get a model. Then you get input data, again, either from the inside or from the outside. You input it into the trained model, then you get a prediction, okay, which is then outputted. This is like the classic way of doing machine learning. Okay, so the first threat is to the model itself, which is an inside threat. If someone has access to the model, he can tamper with it. Okay, he can play around with the model so that it will give a bad predictions. Okay, so maybe it will favor anyone that it wants it to favor. Someone can steal the model and sell it to someone else. Someone can try to extract data from the model itself. Basically, when you talk about internal threats, the sky's the limit. But we're here to talk about external threats. So the first one, and I think the most famous one, is to the input data, right? I think everyone knows the example of a stop sign that if you put a sticker on it, it suddenly turns into a speed limit sign. This is basically evasion, where you change the input data in such a way so that the machine learning algorithm will get confused and will output a bad prediction. That's evasion, okay? Or maybe another example would be someone is trying to block your attack using a captcha challenge, and you somehow manage to trick the captcha or to solve it automatically or to change it to whatever. This is evasion. We basically try to evade the machine learning algorithm and change the prediction. The other attack is training data leakage, right? So in some cases, the training data is just non-sensitive data, right? Just like images of dogs, cats, or something like that nobody really cares about. But in some cases, think the finance sector, the training data is really valuable and really important. So people can try to attack the machine learning algorithm and get it to leak the training data. I think a very naive example is that if someone creates an autocomplete algorithm and it doesn't really do any filtering, someone might be able to put in, let's say, the first 4 digits of a credit card, and then the model will try to output the rest of the credit card, right? Because it learned data from a lot of different users, so it will try to autocomplete the credit card. So that's an example of training data leakage. And finally, we can talk about training data poisoning. So the idea behind training data poisoning is that you play with the training data so that the model will train on data that isn't good, and eventually everything won't work as well, right? The input, it doesn't really matter if it's input or prediction, eventually you get a model that doesn't do what it's supposed to do because the data it trained on isn't good. So how does it work, or what's the idea behind it, and what's the motivation? So this is just a small example of training data, or just data that is being separated by this line over here. And you can see that by simply moving one sample from one point to another, you can see how this separation line really changes quite drastically. Now, this isn't poisoning the data. This is just how much some samples can affect the model or this separation line. Now, here you can see an example of an attack. So before the attack, this line tried to separate between these blue dots and the red dots. Now, what happened is that to the training data, a lot of red dots were added to this point, up to a stage where the model figured out that the best way to separate between the red and the blue dots was to draw this line over here. Now, obviously, this line here is terrible, and this is a very bad model. But as far as like performance is concerned, right, if you check like accuracy or AUC or whatever, you're going to get a high score over here because of all these dots. So from the outside, it will look like this model is doing pretty well, but in reality, it's really not. It's a terrible model. Okay, so let's give some examples of data poisoning in the wild. One of the most easy, I think the easiest example is reviews. Okay, so some sites count on your reviews in order to decide where to place a certain hotel or restaurant or whatever. So if you can just get your buddies to give you a lot of thumbs up, obviously your restaurant is going to be ranked higher, even though that isn't true, even though this is just fake, right? So this is a very simple example of data poisoning in the wild, where someone gets fake good reviews or gets someone to like a bomb review his competitor. And this is a very simple term. It's a very simple example of data poisoning. Another more complicated or more advanced example is this one over here. you see there was a spam group, a group that sends spam, and that's how they make their living. They send spam, and they hope that people will fall for these spam emails. And this group faced a problem because Gmail knows how to block spam. So they thought about a way to somehow circumvent Gmail and manage to reach a point where their spam actually reaches the users. So what they thought about is as follows. Gmail allows you to either label a regular email as spam or the other way around. It allows you to go into the spam directory and say, no, this email isn't actually spam. Now, what this group did is that they opened a lot of accounts and they sent their own specific spam to these accounts. And then they went into these accounts, went into the spam directory, and labeled their spam emails as being okay emails, as not being spam. And over here, you can see these spikes in red. Okay, this red line usually is when someone is manually reporting emails as not being spam. And you can see these spikes over here. And each spike is this kind of a skewing attempt where this group tried to get Gmail to think that their spam is okay, that their spam isn't really spam. Okay, now I think this didn't actually work, but the idea here is that they try to poison the data that Gmail is using in order to classify emails as spam so that they'll be able to send spam emails. Okay, and one final example, which is even more complicated. So this is an example of a computer vision. And what you can see over here is that someone is using an image of a dog. And what they do is that they add noise to this image, noise in the shape of a different fish. So this image over here, you see a dog, but in reality, there's some sort of a fish image embedded in this image over here. And in this one too, and this one too, which is basically invisible to the naked eye, but it's over here. It's inside. Now, what does this cause? If someone created this type of a data set of dogs that have fish images embedded in them, all they have to do, or the other way around, have a fish with a dog image embedded into it, all they have to do is to just upload this data online. Now, if someone will download this data and use it in order to train a machine learning model, what will happen is that they'll open the images by themselves. They're going to look at it and they're going to say, I see an image of a dog, and they'll label this image as being a dog. But in reality, the machine learning model itself, okay, the computer, will see an image of a fish, or both, a fish and a dog. And eventually what this might cause is that when the model will see images of dogs, it will think that they are fish and the other way around. So this is a bit complicated and really isn't that maybe that realistic scenario. But the idea here is that in some attacks, the attacker needs zero intervention in the labeling process. It's enough to create this type of a poison data. And then if someone will use it, it will really affect their model negatively. Okay. So how can you mitigate data poisoning? Well, first of all, you want to filter data from suspicious origins. If you see data coming from any suspicious IPs, suspicious clients, any data that comes from somewhere you don't trust, you can just filter it out. You want to do fault-tolerant data sampling. The idea is that you want to limit the impact of data points arriving from a single entity. So you don't want to take all your data from one single entity. You want to make sure to take data from a lot of different entities. So even if one of them is malicious, it won't cause such a severe impact. Diff tracking, which is detection. You want to look for a significant diff from the previous model. So you have your current model, then you train the new model, and you want to see the difference between the two. And even though you train the new model, you don't expect it to be amazingly better compared to the previous one. So you should see that more or less they act about the same. And another way to do detection is by using a reliable benchmark, which is creating some sort of a model validation, a test suite, for example, using some sort of a data set that you completely trust and checking accuracy in that specific data set. So that if the model isn't good, it won't give you a good score on this golden dataset. Okay, so quick summary so far. Data poisoning is a significant threat and learning mechanism, okay, and from a lot of different ways. The threat is especially critical when you use data from untrusted sources, and there is no silver bullet mitigation, right? There are some things that you can do, but there isn't just like one solution you can use. Okay, now let's talk about securing web applications and APIs, because this is going to be our use case. We're going to talk about poisoning data in this context. So how do you usually secure a web application? One of the common ways is by using a WAF, which is a web application firewall. How do WAFs work? It's actually quite simple. You have your applications and APIs over here. You have the outsiders, or specifically, outside the threat, but the outsiders, the users over here. And in between, you have some sort of a proxy, which is the WAF. Now, this WAF looks at requests coming in from the outside, and it decides which request to forward to your application or API and which request to block. So how do you create a WAF? The classic example is by using a negative security model, which is basically a rule-based model. You create a bunch of rules, a bunch of signatures that look for attacks in the requests. Basically, you're saying that all is good except for what you know is bad. The good thing about it is that it's accurate because you need to manually create these rules and signatures. And the bad thing about it is that, first of all, you have to continuously update it. The second thing is that you're not protected against new attacks, against 0 days. Right? If there's a new attack, you need to discover that attack and create a rule for that attack. Now, another way to go is by using a positive security model. In other words, using anomaly detection. The idea is that you learn a baseline profile for the web or API traffic, and then you block or alert on deviation. So you learn what's normal, and then you block anything that isn't normal. So basically, you're saying that all is bad except for what we know is good. The good thing about it is that you block new attacks, you block 0 days, because basically you block anything that isn't normal. And also you do some sort of a customization for that specific site. You create a baseline, a profile for that specific site. Now, the bad thing about it is that you can get false positives. And the reason is that it's very difficult to distinguish between an anomaly and just a rare behavior, or just bad practice. Okay, now why am I mentioning these two types of model? And this is the important part, because in a positive security model, you need to learn a baseline, and that phase of learning a baseline can be poisoned. Okay, so how do you actually learn a baseline, or how do you learn a traffic profile? And the idea is that you have two types of profiles. You have a global profile and you have a more specific profile. And you can either look at things that happen throughout the site. So host is like the site itself. And then you have parameters that are global, that are the same throughout the sites. And you have headers like cookies and etc. that stay the same throughout the site. And you have some parameters that are a bit more specific. So a specific URL, a host, a specific URL, method, and then either body or query string parameter. But eventually what you're trying to learn is a traffic profile for a specific parameter. It doesn't matter if it's global or not. And what are you trying to learn? You're trying to learn the type of the parameter. Does it appear once or more than once? Does someone have to use the parameter? Is it optional? Is it mandatory? What is the size range? If it's a number, what's the size range? If it's a string, so which char sets are being used for that string? Or maybe what's the number of characters you expect to see, etc. So this is what you're trying to learn. Now, how can an attacker poison this data? So how can an attacker poison this data? I'm just going to give you a small example. Imagine that there's some sort of a vulnerability over here. And in order to use this vulnerability, the attacker needs to send some sort of a string. However, this parameter is normally a number. It's not a string. So if the attacker tries to send a string, it's going to be blocked. But if the attacker will constantly send a string over and over again, at some point, our machine learning model might think that maybe strings are okay, and it will add to the traffic profile that strings are allowed to be used, and then the attacker can send this exploit and hack the website. So how can you stop this? So it's a bit similar to what we talked about before. We want to filter traffic coming during suspicious events, traffic from suspicious IPs, traffic doing attacks, and traffic from bots. And another thing we want to do is use threshold learning. So what is threshold learning? And this is important because we're going to talk about it a lot. The idea is you want to learn only what you see in multiple requests. So if you see something that comes from a lot of different IPs and a lot of different user agents, a lot of different geolocations, a lot of different clients doing different hours and days, and so on and so forth, you can trust it more than something that you see coming from one specific IP, doing one specific hour 100 times. You want to make sure that the data you see comes from a lot of different sources. This is what we talked about previously, that you want to limit the impact of a single entity. So you want to make sure that you learn from a lot of different entities. Once you finish your learning, you can do the enforcement, which is alerting deviations from the profile. So this is easy in batch processing, right? You just take all the data, do some group bys, and count the number of unique IPs, unique user agents, etc. But if you have a site that has significant amount of requests, a significant amount of traffic, this won't really work, right? Because it consumes a large amount of memory, and it won't work when you talk about huge sites. Or at least you'll have to use crazy machines, which we really don't want to do. We want to find some sort of a streaming solution. Okay, so we're going to talk about the streaming solution, and we're going to illustrate it using dog food. So this is also an illustration of why it's important to limit the impact of specific entities and why it's important to do this type of a threshold learning. So over here in this example, you can see how many different dogs from different cities thought that these specific dog foods, Tio and Pedigree, are tasty. So if you just look at the results, you can see that Tio got 9 likes and Pedigree got 6 likes. So one would think that Tio is the better dog food. But if you actually look at the data, you can see that basically the only dogs that like Tio are New York Pomeranians. These are the only ones that like it. The rest of the dogs, Pomeranians from San Francisco, St. Bernards, German Shepherds, etc., they all like Pedigree. So eventually what one would think is that if they would use Tio, they would just, not all dogs like Tio, just New York Pomeranians. So it's better to actually use Pedigree even though it got less likes. So this is the idea behind threshold learning. We want to make sure that whoever said that this dog food is tasty, we want to make sure that they came from a lot of different cities and a lot of different breeds, so that we don't allow one single breed from one single city to have too much of an impact. Okay, so in this example, Pedigree is the one that wins because you can see all these different cities and different dog breeds that actually like it. Okay, so let's try to do, now this is kind of a batch processing. Let's try to do the same process, but online. So how do you do threshold learning? How do you see how many cities and how many breeds actually liked this dog food by working in online manner instead of batch processing? So the idea is as follows. You have the objects, Pedigree and Tio. You have the facts you want to learn about these objects. Okay, is it tasty? Is it nutritious? Then you have the attributes, which is basically the thresholds, what we care about. Okay, what we want to see that there's more than one. In this case, we want to see at least 3 different cities and 3 different breeds. And these are the sets. So I'm going to explain it using an example. Okay, so this is our data. Now we start with, imagine the data is going through, and at least now we're just going to look at the number of breeds that think that Pedigree is tasty. Okay, so in order to learn that, all you have to do is count the unique values of breeds that think that Pedigree is tasty. Okay, so it's a very small data set, just 3 values over here. Okay, and now this changes from an X to a V because we met the threshold. We can see that at least 3 different breeds like Pedigree. If we do the same thing, so if you look at the cities that like Tio, all we have to do is remember the number of cities that do that, which is just the one, okay? And it didn't pass our threshold over here because we need to choose 3 different cities. Same goes for the breed. And if we go back to pedigree, we can see that there are 3 different cities that like pedigree. This gets the V as well. And now we can finally decide that a pedigree is actually tasty and that we trust this fact because we can see that these thresholds were met. So basically the idea is that you get this data line by line, and then you just go through it. And let's say the first line is New York Pomeranian. We talk about Tio, and someone thinks that Tio is tasty. So you go here and you say Tio is tasty. And then you just count how many cities you saw and how many breeds. So the idea here is that if you look at this, you can see that there isn't a lot of memory you have to hold in order to maintain this table. So let's run a quick summary. You can learn Boolean facts. You can learn things, the type of object X as property Y. In our example, you can say pedigree is tasty, okay, a Boolean fact. And this way, the memory consumption is proportional to the number of objects and number of properties. It's proportional to the number of thresholds, but it's independent of the size of the data. Because basically, all you have to remember is the different sets of the attributes you care about. So in the previous example, the number of different breeds you saw, the number of different cities you saw. Okay, so you can learn these type of Boolean facts, and then you can also enforce them. So let's show a quick example because this isn't that clear. And also you might be wondering, what can you actually express with Boolean facts? So there are a lot of things you can express because we just want to ask if something appears or not. But when you talk about a website, you can ask, does this host has URL X? Okay, so which different URLs are in this website? You can do that, okay, by asking if a certain URL exists, doesn't exist in the website. You can ask about the different cookies, different methods. You can ask about the different query string parameters. Do they appear or not? Does this website have these parameters? And so on and so forth. Basically, you can easily create a map of the website using these Boolean facts. Okay, but you can go even further. You can talk about data types, ranges, char sets, regular expression, etc. You can use Boolean facts, okay, to discover the type of a parameter, because you can ask, did we see numbers for this specific parameter? Did we see non-numbers? Did we see strings? Did we see nuns, bool? Did a male regular expression match this parameter? And so on and so forth. You can even talk about if a certain parameter is missing, if it's allowed to be missing, if it allows to repeat more than once. Okay, you just have to ask these questions in this type of yes or no answer, and there's a lot of different questions that you can ask. Okay, basically you can say that it's taking these values and creating a one-hot encoding. So let's kind of explain how this actually works. So let's say you want to decide, you want to see if a certain parameter is the mail address. Okay, so what will happen? You will learn over time that string type is allowed for this parameter. You will learn that it matches a male regular expression. Okay, and you also want to learn that non-male regular expression is prohibited. But you can't really learn this because there's no way to learn that something isn't allowed. Okay, but you can go the other way around. You can say, I never learned that non-male regular expression is allowed, and so I can reach a conclusion that non-male regular expression is prohibited. Okay, and if let's say we talk about mandatory parameters, so you can learn something is optional because you can see that it was missing at some point. Okay, so let's keep going. You can go even further. You can talk about sets and ranges. So for a specific parameter, you can learn if you ever saw a non-letter in the parameter, and the parameter value is if you saw non-digit, non-hex, etc. You can even say if you saw a specific ASCII character. Okay, and you can also talk about length. So you can it has to be in a discrete manner, but you can talk about length. You can look at the parameter and you can say, did I see that it was this value was longer than 5 characters? Did I see that it was longer than 50 characters, 500, etc.? Or you can talk about the size of the parameter. Was it greater than 10, greater than 100, etc.? And you can do some very nice things with that. So let's say, for an example, you can learn that a parameter has a char set of base 64 because you saw that strings are allowed and that base 64 is allowed. You saw strings and base 64, but you never saw non-strings and you never saw non-base 64, so you can reach a conclusion that this parameter is a base 64 parameter. Let's say you want to learn that the parameter has all the alphanumeric characters plus colon and semicolon. Okay, how do you do that? You will learn that strings are allowed, you will learn that alphanumeric is allowed, and you will learn that these two ASCII characters, the colon and the semicolon, are allowed. On the other hand, you won't learn that non-strings are allowed, and you won't learn that all the other ASCII characters are allowed. Okay, and eventually you can reach a conclusion that this is the char set, alphanumeric plus these two. Let's talk about the parameter length. Okay, so this is a bit more tricky. So let's say parameter length is between 35 and 345. You will learn that string type is allowed. You will learn that length greater than 5 characters is allowed and length greater than 50 is allowed. On the other hand, you won't learn that, sorry, this is a mistake, but you won't learn that the length greater than 500 or 5,000 is allowed, and you won't learn that less than 10 characters are allowed. So if you think about it a bit, what eventually you understand is that anything between 10 characters and 500 characters is allowed. By looking at all these different values, that's what you will eventually learn. So you can't be as specific as 35 to 345, but you will learn that anywhere between 10 and 500 characters is okay. Okay, great. Now, sometimes this isn't enough, right? In some cases, you can say this traffic profile really isn't enough. I want to learn more. I want to employ some heavy machine learning algorithms. I want to do something that is a bit more complicated. But you can still use this system. And why is that? Because imagine this is the scenario where we talk about the login URL and specifically the body parameters, which is, let's say, where the username and password is sent. You want to use some sort of a special machine learning algorithm so that it will discover account takeover attacks, for example. Now, once you start running the system, you'll see how many different requests go throughout your website. You can see that, let's say that you get 200 requests per second, and they split as following: 50, 40, 80, and 30. Okay, and eventually for these two get and post, you get 40 and 40. Now, you can look at this data and the number and how much load is on each URL and decide, do you have enough resources to use an advanced machine learning algorithm? If you do, then great, use it. If you can't, you can use this type of Boolean facts. The idea is that by using Boolean facts, you can quickly cover all your website or most of your website, okay? And if at some point that isn't enough, you can always just use whatever advanced machine learning algorithm you want to use. So let's do a quick summary and conclusion. First of all, data poisoning is a significant threat on learning mechanisms. And we went anywhere between the reviews example, where someone just review bombs a competitor, or where someone gets people to give him a very good review. And this is one way of data poisoning. We talked about another example where someone tried to mess around with Gmail's spam filters. Another example was the one with the images. But the idea is that if someone can poison your data, this can cause a lot of trouble. On this example of a web and application APIs, web and API, what can happen over here is that someone can mess around with your baseline so that you won't be able to accurately do anomaly detection. Okay, they'll basically insert these anomalies into your training data and make it very difficult to detect anomalies along the way. Another thing we talked about is how threshold-based learning may provide an adequate, robust learning solution, right? Because you make sure to only learn things that you saw from a lot of different resources, it will really prevent the chance that you will learn something from one specific attacker. If someone is just trying to poison your data and he isn't going to very great lengths to make sure that this poisoning happens, you will be able to filter him out by not considering anything that comes from like 1, 2, or 3 different entities. You want to make sure you learn something, you learn a fact only if you see it coming from a lot of different entities. Another thing is that this Boolean facts framework, the one we just talked about, provides a streaming-friendly implementation for threshold-based learning. Okay, so because you learn Boolean facts, because you don't try to basically learn everything, because you try to learn very specific facts, you can do it in a streaming manner, which is very memory friendly. And finally, there are a lot of different features that can be expressed with Boolean facts, even though you're basically just asking yes or no. By looking at what you learned and what you didn't learn, there are a lot of different things that can be expressed by using Boolean facts. Okay, so thank you very much for joining me, and I would love to hear your questions now.
Awesome. Thank you so much for this talk. I think it was a really important one, and also I've learned tons. We have at least one question that I saw, but in the meantime, I'm also curious because you talked about dogs. Are you a dog person?
Yeah, a bit. I always had a dog, so I have a dog for now, and yes, definitely a dog person.
What kind of dog, and do they like pedigree?
Well, we don't have pedigree here, so I don't know. I'll try if we get some. He's a shelter dog, so a Labrador with something. Don't really know.
Oh, okay. Those are the best.
Yeah.
You get a lot of points for that one. All right, let's go for a serious question from the audience. One from Azaria is, can we understand the data poisoning affecting primarily AI models that follow a real-time or near-time life cycle, in the sense that they constantly try to improve their prediction with every new data point entering the system? And if yes, what are your thoughts on security of such models following a less frequent update process that includes human supervision? It's a long question. Did you get it?
Yeah, okay. So first of all, no, it affects everything. Data poisoning, I've shown the example of someone can just poison data and upload it online, and if someone will accidentally download it, so they'll have a poison data to use. So it's not necessarily real time, but basically any model can be affected by data poisoning. Obviously, if all your data is in-house and you do everything in-house, so there's a very low chance that you'll be affected by it. And if you don't retrain the model over time, so there's less of a chance of being affected by data poisoning. You are right that if we talk about things that like real time, look at the data in real time and then constantly retrain that data, you're probably more susceptible to data poisoning. I think that using humans in the process can be a very good solution, using some sort of a human in the loop, where basically anything that doesn't make sense, something that doesn't look so good, instead of using it, you can send it to a human that will either validate it or not. That can be a good solution. Another thing can be basically what we talked about over here. You will only retrain if you see this example coming from a few different resources. Okay, so if you see a few different entities giving you this data or giving you this answer, you can retrain. But if you see it only coming from one place or two places, one or two entities, so you won't add it to your database.
Perfect. Let's take one more question. How do you tackle the topic of representativeness between development and application population of the model, or avoid bias in productions for a certain subpopulation while using threshold learning? Is this somehow embedded in the threshold definition?
Okay, so this is actually a great question, and it's a problem. I can't say that it isn't a problem. Just to kind of repeat, one of the issues is that when you talk about threshold learning, what we're basically saying is that we'll only consider something that is a kind of a consensus, right? If you see it coming from a lot of different entities. But in some cases, things are just rare, right? Only a few persons, only a few people use them, only a few people try this type of stuff. So you won't see some of the data coming from a lot of different entities, but still that data isn't poisoned. So that is a problem. It isn't directly represented in threshold learning. I can't say have a straightforward solution for that. That is like where you have to work a bit harder. But no, it doesn't. It isn't part of the threshold learning solution.
Awesome. Well, thank you very much again for your talk, and that's it for today for this track. And we'll see you all tomorrow again. Thank you so much.
Okay, thank you.
Bye.